All right, 10.7. We're finally starting to get into the interesting part of series. The whole purpose of learning series here in Calc 2, power series. And then this is going to extrapolate into Taylor series if you've ever heard that before. So let's jump right into it. So first off, a quick definition. A power series about x equals 0. So there's always going to be the starting location. Here we're starting at 0. Is a series of the form this. So an infinite series, we'll just start at 0. Usually for power series, you're starting at 0 to infinity of some constant value. This constant changes with every term, x sub n. So basically what we're doing is we're just adding up a bunch of the different power functions. By a power function, we're just talking about a constant and then x to some power. So we're just going to have a constant number out in front, c sub 0, and then c sub 1, x to the 1. There we go. Plus c sub 2, x squared, plus c sub 3, x cubed, and this is going to go on forever. So a power series is basically an infinitely long polynomial. Cool. We don't always have to start at 0, so let's look at another power series. This time let's start about x equals a. So for this one, it's a very similar definition, still going to be going from 0 to infinity. The only difference is that you're going to have an x minus a inside. You can kind of think of it like you're taking this infinitely long polynomial and we're just shifting it to the right a units, or to the left if it's a negative a. Okay, a little bit more with this. We say that this has a center a and coefficients with center a and coefficients, those c sub n's. Great, so let's just look at a quick little example. Hopefully this will blow your mind. Let's look at just the most generic power series that we can think of where all of the coefficients are 0. So if we go from 0 to infinity of just x to the n, if we were to write this out, this would be 1 plus x squared plus x cubed plus forever and ever and ever. Okay, so this infinitely long polynomial, this power series, if you want to think of it this way, this actually converges to something. We know this converges to something because this is kind of like a geometric series. It's a geometric series where our r is this x. So as long as this x value is a number absolute value wise that is less than 1, this is going to converge. And we know what it converges to because of the power series thing. So this is geometric, and as long as the absolute value of x is less than 1, we get convergence to 1 over 1 minus x, right? Because our a value is 1, our r value is x, so this is going to be the limit or the sum of this infinitely long power series. Okay, so what makes these power series so powerful is we want to think about this the other way around. Instead of just writing out a power series and figuring out what it converges to, we're going to do it backwards. We're going to be taking functions, usually pretty awful looking functions, and trying to figure out, is there a power series that goes to that function? The reason for that is because this is very difficult to differentiate and integrate. Right? If I were to integrate this, it would be some awful natural log stuff. But this, just a polynomial, is very easy to integrate. That we can integrate with no problem. Cool. So, whoa, I'm dropping stuff off my desk. It's all right. Moving on. That's how excited I am. I'm just throwing stuff everywhere. Consider this. 1 minus 1/2 x minus 2 plus 1/4 x minus 2 squared plus all the way down to the nth term 1/2 to the n x minus 2 to the n. All right, this is also geometric. With so our r value is a little bit tricky for this one. Remember that for geometric series, the r value is whatever you multiply by each time. The thing that we're multiplying by each time is every single time we're multiplying by a 1/2, and we're multiplying by an x minus 2. So that's going to be our r value here. The a value is just 1, right? Don't forget for these geometric series, whatever the constant is out in front, that's going to be the a. This converges as long as that absolute value. So I'm going to go ahead and distribute that negative 1/2 into the parentheses here. So absolute value of x minus 2 over 2 is less than 1. Okay, so that negative sign out in front, I just took that away inside the absolute value as well. So we can solve this. So I know it's probably been a while since you guys have done absolute value inequalities. The trick to doing these absolute value inequalities is you want to squeeze the inside of the absolute value between the negative and the positive of the constant on the other side. So we're going to squeeze this between -1 and +1. This we can solve. We're going to multiply both sides by 2. And then add 2 on both sides. So we get this. All right, this is going to be something that we're going to define later, but you can think of it like this is where the series converges. This power series here will only converge as long as we're plugging x values between 0 and 4. Okay, we can find the sum as well. So if we are plugging in numbers between 0 and 4, and then don't forget this is geometric, we can find the sum by just doing a over 1 minus r, the geometric series sum. Remember our a is 1, so it's going to be 1 over 1 minus, and then that awful looking r value, which was, how am I going to write this? -1/2 times x minus 2. Does that look all right? Like decent? Looks okay. So you can simplify that down a little bit. I'm not going to do some algebra here. Just note that this simplifies down to be 2 over x. So in other words, again, 2 over x is the sum of this awful looking power series. Now, I know the question's probably like, well, 2 over x doesn't look that bad. Why do I need this written out in such an awful looking way? And again, that's because polynomials like what we have here are just so much easier to work with in calculus than things like this, rational functions. Right here we have this awful asymptote. We're not going to have an asymptote inside of this polynomial. Okay, I do want to show you that this does actually work. So let me get this set up. I'm going to pause the video and come back. Okay, so I think I got it set up the way I want it. So here we're in Desmos, and what I've done is I have graphed that sum, right? Remember the sum of that power series was 2 over x, so that's the red graph here. I'm also graphing the power series itself. I'm starting at just 0, and it's going to go all the way up to the first 10 terms. So first, when I hit play here, it's just going to graph the first term. Then it's going to graph the first 2 terms added together, then the first 3 terms added together, and so on and so forth. What we're looking for here is that, don't forget, the power series comes out to be this sum. You want to think of it like the power series is approximating this curve. Here we go. All right, so this green line is just the first term when k is 0. If I then add the second term, I get the next approximation for the power series. So this is just the first 2 terms added together. It's not a great approximation. But as I keep going and keep going and keep going, notice how the green line starts to mimic the red line practically perfectly. But it's not doing it everywhere, right? The only location where the green line is replicating the red line is in that interval between 0 and 4, where the convergence of the power series takes place. But isn't that just the coolest thing ever? That these power series, this polynomial infinite series, approximates the function 2 over x practically perfectly on that interval between 0 and 4. Okay, that is the whole purpose of this next few sections here. All right, going back to our document though. I do have one quick example that I want to do before we jump into the next video. All right, so one more example. Let's look at this question. For what values of x does the power series converge? where this is our power series. So we're looking at the infinite sum. We'll go from n equals, we'll start at 1 this time to infinity. Oh, not 0, sorry, infinity. Of the alternating x to the n over n. There we go. Whew, got it. All right, so just to write a few of the terms here, this is going to be x minus x squared over 2 plus x cubed over 3, and then so on and so forth. Okay, this is an alternating series. Also, it's kind of close to the harmonic series, but just with this x to the n kind of up top. So it's all depending on what happens with this x to the n on whether this is going to converge or not. So this is an alternating series, and we could use the alternating series test to figure out where this thing converges. But 99% of the time, I want you to use the ratio test. The ratio test is really going to bog down where the convergence is happening. So almost always do ratio test when they're asking for where does a power series converge. Okay, so if we do the ratio test, remember that's the limit of the absolute value of the n plus 1 term divided by the nth term. So let's look at the n plus 1 term. That's going to be negative 1 just to the n, and then x to the n plus 1, that divided by n plus 1. I'm going to go ahead and rewrite that division as multiplication of the nth term flipped over. So that's going to be an n up top, and then a negative 1 to the n minus 1, and then x to the n on the bottom. Close the absolute value. All right, so this is the n plus 1 term divided by, or in this case, multiplied by the reciprocal of the nth term. All right, so first things first, these negative 1s are doing nothing, right? Because they're inside the absolute value, it's going to make it positive regardless. So we can just ignore the negative 1s. Then I have an x to the n plus 1 up top, and then just a regular x to the n on the bottom. We're going to use that trick that we saw back with the ratio test. We're going to write that numerator, this, as x to the n times just a single x. What's going to happen is that the x to the n's are going to cancel. I'm going to have a single x up top, and I'm also going to have that ratio of n over n plus 1. Okay, so just pulling the x out, and we still have n over n plus 1 left over. Remember that we're taking the limit as n goes to infinity. This x is just a constant as far as this limit is concerned. So we could pull that out of the limit. Then the limit of n over n plus 1, we've done this so much at this point, I hope you can see that that is just going to be 1, which means that this approaches the absolute value of x. Don't forget that x, we don't know if it's positive or negative, and it is inside the absolute value, so it has to stay there. But we did this using the ratio test. And remember that the end of the ratio test, this value that we got, that's that row. And as long as this row is less than 1, we have convergence. So we're just going to make the row be less than 1 by setting it to be less than 1. Again, we have the absolute value inequality, so we're going to squeeze that between the positive and the negative. This is going to be my final answer. This power series converges as long as my x is in between negative 1 and positive 1. These can get a little bit more difficult, so we're going to look at a more difficult example in the next video, and then a few theorems.